Hi everyone. In today's video, we are going to go through all the 4G and 5G technology differences, and I believe this is one of the most important sessions, especially if you just started studying 5G and you have a good knowledge about 4G, because this can be a warm-up session for you to get quickly engaged in 5G technology, because this one will spot the main differences between 4G and 5G and will get you yourself familiar with 5G technology. And also, it's as you know, this is one of the main interview questions was being for an interview, especially 5G interviews, which might be asked by the interviewers. So it's good to focus on this session because it's really very good one and it's very important. Let's go forward. Okay, the content of the day session will be covering those points. First one, the differences in RAN structure, then the difference in quality of service between 4G and 5G, then the main difference in radio protocol stack, especially with more focus on the user plane, and then we'll go through the frame structure and the bandwidths. Then we'll go through the main difference in physical channel and physical signals, and lastly, will be ended by the main differences in the link budget. So the first part, we'll go through now the RAN structure. Let's start first with the RAN structure differences between 4G and 5G. Here in this slide, I'm showing three main structural architecture. First one for 4G, and this is mainly from the access network or from the RAN side. The first one is showing the 4G, the second one showing 5G non-standalone option 3X, and last one showing 5G standalone option 2. As you remember, in 4G it was very simple. Like we have a connection between the two unit Bs with the X2 and the air interface to the UU interface, and this one interface with the MME and the SGW serving gateway. It can be like user plane and control plane separation. And the same, almost the same in option 3X, because option 3X it's like for the 5G non-standalone, which is still relying on the 4G side, 4G architecture. However, there was a many change in the 5G standalone, like the MME and serving gateway has been replaced by AMF and UBF. From this part, it looks like very similar. Yeah, for example, XN replaced X2. You have NG interface replaced an S1 interface. The error interface kept the same, and so on. Here it looks like very, very similar. However, in fact, there are a core difference and change introduced in 5G if you logged into the higher level of the complete or full 5G architecture. So let me now take you the complete 5G architecture to be able to spot the differences, which is very important to know about it, because this will make you like having clear understanding about uh, why these differences has been introduced in 5G. So let's move to the next one. Okay, moving forward, this is the full architecture of 4G and 5G standalone. Here in the left, this is for the 4G part. This is showing the complete architecture. If you remember that we have the UE, LTE, still air interface, and we have X2 between different NLBs or different 4G sites. Then we'll have the user plane towards S1U toward the serving gateway, and we have the control plane through the MME. MME is being connected to HSS, and then we have the serving gateway connected to the packet gateway, BDN gateway, and packet gateway is connecting us to the external internet to the internet through the CGI interface. So here, if you can see that we have the serving gateway and packet gateway, and packet gateway actually it's having two main responsibilities, which is first one for IP allocation, okay, which is means control plane, and the second part that's relating to data forward or packet forwarding towards the serving gateway and so on. So this means that here in this part, still we have two main functions, control plane and user plane. Okay, now let's go quickly through the 5G architecture, especially with more focus on the RAN access side. Again, here, this is the complete architectures. Many new entities has been introduced. We'll not go through it. Many of it like related to network slicing and so on. So let's first try to spot the differences to the 4G architecture. So you can see here you have the user plane as example. Now it's connected to the 5G access network, which is the G node B. Then the G node B is being connected to the UBF through the N3 interface. Then this one is the user plane now is being connected directly to the DNN or data network through N6 interface, which is similar to packet gateway. However, the main point here that this part is only responsible, or UBF is only responsible for the user plane. all for example, here only will be for packet forwarding. However, the IP allocation function, which was part of the control plane, has been allocated to a new function or new entity called SMF, session management function, which will be responsible for the IP allocation. Okay, so what it means by this? It means that in 5G now, that there is a separation between, or the 5G has separated the user plane and control plane, function, which actually this is different from 4G original architecture, as we just highlighted. Okay, just to recall it again, just to explain it more. As you can see here, we have the 4G packet gateway. It's providing two main functions, which is control plane IP allocation, address allocation, and user plane, which is packet forwarding. While in 5G, this has been separated. The UBF will be responsible for the packet forwarding, and the SMF will be responsible for provide IP allocation. And actually, this separation it's allows independent scaling of of two main functions. The first, if you can see it, the first one, that the operators now can add more user plane capabilities without having to add a control plane, additional control plane. Since we have a separation, so now we can add more, the operator can add more user plane capabilities to the network, and actually distributing the user plane in this case can be distributed, while we can keep the control plane as centralized. And distributing the user plane can help the operator, or help them to keep the UBF or the user plane function geographically close to the access network, like to be in the same city, like just to make it as close as possible. And actually, this can help to minimize the network latency. And this is one of the most important factors of having this kind of architectures, which will help to minimize the latency in the future. Because actually, as you know, like especially in the very big cities, that we have this kind of challenges that locating the core network where it's locating sometimes is very far away from the cities. So now we can have this kind of flexibility to have the distributed UBF or user plane function, which can help to minimize the latency. And this is the main differences if you are talking about the RAN radio access side, and also the overall 5G architectures. As mentioned, we have a lot of other function has been added for authentications, for network slicing, application function, and so on. This we can go through the details later on in a different section. Yeah, and that's it for this part. Let's now move to the quality of service differences. Here we'll be addressing, we're speaking about the difference in quality of service between 4G and 5G. Initially, I will take you through the 4G quality of service structure or architectures to show you how the peer are being established, who's responsible for the quality of service mapping, and so on. So initially, assume that you have a default bearer, which is going to be established. Let's assume CI9. So initially, you will have a connection between the U and the NLB through the radio bearer. Then you will have the S1 bearer between the inode B and serving gateway. Then you will have the S5, S8 bearer between the serving gateway and packet gateway. And as you remember, for sure, the radio bearer plus S1 bearer is called ERAP. Then after establishing the S5, S8 interface or bearer, then we'll be establishing the external connection with the internet, which is called external bearer, and this is through the ABN access point name. So now we didn't address or highlight the quality of service. Okay, now all this combination, which is radio bearer, S1 bearer, and S5, S8 bearer, it's called EBS bearer, and this is responsible to establish end-to-end connectivity between the U and packet gateway. Okay, what it means this one? It means that the 4G uses the EBS bearer to provide end-to-end user plane connectivity between the user plane and the packet gateway, or we can say it, and the ABN access point name within the packet gateway. And this ABN access point name, which you usually get it during the initial or during getting the default bearer, ABN defines the interface to the external data network. And this external bearer, this defines the interface. So this overall called end-to-end service bearer. So now again, to rephrase it, the EBS bearer is responsible for the quality of service mapping. However, the main point which I want you to keep it in your mind, that in 4G EBS bearer can only have one-to-one mapping to the quality of service. Okay, this point is not very clear, so let me make it more clear for you. It means that one-to-one mapping, for example, let's assume that now we have default bearer quality service 9. Okay, let's say I have quality of service 9. So in this case, once let's say you have QCI 9. So let's assume that you want to establish a new QCI. Let's assume QCI 7, QCI 6, QCI 5. So in case if you want to have a new QCI, in this case you need a new EBS viewer, which means that you need to establish again the complete connections, which we just mentioned here. So let me, for example, take you through dedicated viewer. Let's assume that you have QCI 5 in order to start establishing the VoIP call and whatever, or IMS. Okay, so in this case, once you have the dedicated viewer, you will have again the complete connections, which is starting from radio viewer, S1 viewer, S5, 8 viewer, and so on. This means every time you'll have a new QCI, you will need a new ABS viewer, and so on for the same user. And this is the main point about 4G. Now let's go through the exact same in the 5G quality of service to be able to address the differences and why we have such a difference in 5G compared to 4G. Initially, again, you will have the distributor, which is exactly the same. But if you can see here, the UBF here, you have serving gateway and packet gateway. Here only you have UBF, as mentioned here in this part. Then you will be establishing the N3 tunnel between the Unit B, which is N3 interface, between the Unit B and UBF. Then you will be starting communicating with your external network, your external network, or establishing the external barrier between the UBF and the data network, or the beer entity, or the internet, or whatever the name, just the external name. Okay. Before we mentioned in 4G that we have the ABS peer having like it's making the mapping with the quality of service. In 5G quality of service, it's called video session. We have the video session actually is responsible for the mapping. 5G uses video session to provide end-to-end connectivity again between the UE and the DNN, which is called data network name, similar to the VPN. Within, and this DNN, it's within this mapping is done within the UBF user blame function, and again this DNN, or the data network name, it's defined in external interface with external peer. Okay, so far what I can see, it's almost exactly the same. There is no major differences. So now let's simulate that if you are receiving some like, for example, services with different quality of service. Assume that you have now a Skype video call. This Skype video call is being established using, for example, quality of service flow, or if you are talking about quality of service flow, let's assume 5. Then the first point that UBF need to map this quality of service to map this Skype services quality of service 5, for example, to this quality of service 5. The UBF is responsible for this kind of mapping. So the first thing that the UBF will inform the Unit B that this kind of service is using QFI5. Then the Unit B will be responsible to map this QFI5 or quality of service flow 5 to a specific radio bearer, and this is done through a function or through a layer called SDAP. We'll speak about later within the Unit B. Okay, so the main point here that you have Skype using QF quality of service flow 5 is being mapped to this radio bearer. So far, okay, now assume that you have a YouTube, and this YouTube is using quality of service flow 4. So who's doing the first mapping? First mapping will be done through the user blame function, and this, as you can see here, again, it's established or mapped to the exact same radio bearer. And here where the difference came, that still you have a different, you can have a different quality of service, multiple quality of service mapped to the same radio bearer. And this is the main point here, that the video sessions support one or more quality of service flow. Okay, and it's not necessarily that this quality of service flow to me be mapped to the same radio bearer, same as what we have mentioned here in 4G. In 4G, no, you can have multiple quality of service flow for the video session mapped to the exact same radio bearer, and also still you have the flexibility to map only one quality of service flow to one radio bearer. And let's assume that you have a new video session here with a voice call. This voice call, as you can see here, a new video session, let's assume video session 2 or whatever, and this voice call is being mapped to quality of service flow 1, and now it's like mapped to the radio bearer. So here again, just to rephrase or to recall the summary, for the 5G, the video session is responsible for the quality of service flow, and it will be mapping the quality of service flow or responsible to establish the complete connection between the UE and the UBF. UBF is responsible for the first mapping towards the Unit B. Then Unit B will be mapping this quality of service flow to a special radio bearer. And the main difference is that in 5G you can have multiple quality of service flow mapped to the same radio bearer, while in 4G you have EBS bearer having one-to-one mapping with the quality of service. This means you can have only one quality of service mapped to one ABS bearer. You cannot have more. If you want more, you need to establish a new ABS bearer. And this flexibility in 5G, it's actually as an introduction for the network slicing that you need to have this kind of services, which we can be explained later on in next sessions or another sessions. Okay, now I mentioned here one point related to that, how the Unit B is doing the mapping to a radio bearer within one layer called SDAP or SDAP. This one will address or spot it in the next slide, which is related to the protocol differences, especially in the user plane between 4G and 5G. Let's move to the next slide. Okay, moving forward, this is actually the radio protocol stack SDAP layer, which is being added here in user plane, as mentioned here. Okay, now let me address the differences between the user plane, the radio protocol stack. In the 4G user plane, we have from the UE and the UNIB side, we have 4 layers, as you know. First one is PDCB, then we go into RLC, MAC, and physical. While in 5G, there is one additional layer has been added called SDAP layer, and this is SDAP stands for Service Data Adaptation Protocol, and this actually, as I mentioned in the previous slide, that this one is primarily, or the primary function of SDAP layer is mapping each quality of service flow into a specific radio bearer. And as mentioned again, that we can have multiple quality of service flow mapped to a single bearer, or we can have one-to-one mapping. And here, this is as you can see here, for example, that you have a PDU session. This PDU session having quality of service, like for example, 3 quality of service. 2 of them has been mapped to data radio bearer 1, and 1 has been mapped to data radio bearer 2. This is within this PDU session having 3 different quality of service. So this is actually the main function of here, and here is the summary. And there is one more important note you need to consider, that every time you have quality of service belonging to a different data radio bearer, as mentioned here in the last line, this means that you should map it into a different DRP. So each new video connection needs a new data radio bearer, and let's move now to the next part. Okay, now let's highlight the main overall technology differences or key technology differences between 4G and 5G. Okay, the first part is in the bandwidth. As you know, that 4G was supporting for one carrier, supporting up to maximum 120 megahertz. Now in 5G, we can have 2 different frequency ranges, which is frequency range 1 and frequency range 2. Frequency range 1 can be up to 100 megahertz, and frequency range 2 up to 400 megahertz. And frequency range 2, they call it millimeter wave, and frequency range 1, it calls sub 6 gigahertz. And also there is a new concept was being introduced in 5G called bandwidth part. It's called bandwidth part, and this is also one of the core differences, and have many different applications whenever we go through the details later on, that it can provide, like for example, if some is not supporting the full bandwidth, supporting small bandwidth, it can be assigned only for those, for example, 20 megahertz out of 100 megahertz and so on, just as an example. And also it's beneficial for battery saving and so on. So this is one of the things which is being introduced in the bandwidth part. So we can just summarize this point, that that the 5G offers much higher, up to 10 times higher spectrum compared to 4G. This is one of the main differences in the bandwidth. Secondly, it's about the numerology. Numerology, actually, this is system parameters, and it refers to the SCS, subcarrier spacing, and its related parameters, such as the symbol length and the cycle prefix and so on. Okay, what is the main difference and what this means? The first of all, the subcarrier spacing, if you remember, it was fixed in 4G. It's 15 kilohertz. All the time it's 15 kilohertz. It's fixed. It cannot be changed. And in 5G, we have the transmission to time interval was only 1 millisecond, and also it was fixed. Now actually it's different. Now we have flexibility in 5G. 5G is presenting sub-carrier spacing from 15 up to 240 kilohertz. However, 240 kilohertz is not used for data. That's why I didn't highlight it here. So we have in SCS in 5G, we have 15, 30, 60, and 120 subcarrier spacing. And actually, the main point about the subcarrier spacing, that different subcarrier spacing can offer different coverage and different latency. Because actually, the main point about the SCS, that the symbol length is mainly relying on the SCS. The symbol length is equal 1 divided by SCS. That means all the time, whenever you have in higher SCS, you will have less symbol length, and accordingly your scheduling time will be much less. For example, in 30 kilohertz, the scheduling LTE is very slow. For example, in 30 kilohertz, we have the transmission time interval is only open 5 milliseconds, which is half the 4G, which means that, for example, as an example, this one can improve the latency. You can have quicker scheduling and so on. So this one can improve the latency. This is one of the things. So this is for the numerology part. Now going through the broadcasted channel. Actually, in 4G, the broadcasted channel, first of all, it was transmitted through wide beam. Yeah, I will go through one by one. I will try to simulate in the next slide, but I'm just like addressing here overall the points first before going into the details. So the broadcast channels, it was in 4G wide beam. Now in the 5G, it's the broadcast is being transmitted narrow beams. This is something called SSP swapping, because now in 5G, the broadcast channel is part of the SSP. Excuse me. It's part of the synchronization signal block, and that's why I have this beam swapping, which being introduced in 5G, which can result in narrower beam, and for sure it will accordingly it can improve the coverage and also the quality, and also we'll addressing this part in next slides. For the reference signals, it was like in 4G, it was called cell specific reference signal based. If you remember, the channel demodulation was based on cell specific reference signal, and we call it always on. Always on means because it's all the time being transmitted, all the time. So that's why it's called always on. However, now in 5G, the first advantage is that we don't have CRS. CRS is free. We don't have any more CRS. No more fixed cell-specific reference signal. Now we have CSIRS, a channel state information reference signal, and demodulation reference signal, DMRS, based, and both still used to demodulate the channel condition and so on. And actually, it's offer much better performance compared to the CRS. The next part, it's about the PDCH resources. In 4G, the PDCH resources was in the frequency domain. It was like distributed over the entire bandwidth. You don't have any control over the frequency domain. Now in 5G, it's introduced something called core set. This is a new concept in 5G, and this is giving more control over over the frequency domain. You can having configurable, you can reduce, and like based on according to the 3GPP specification for sure. And this one actually it's also introduced because of to accommodate also with the bandwidth part, because bandwidth part can be much less compared to the like for example the original or the completed channel bandwidth. Okay, next part it's about the PDCH. In 4G we used to have long format. Now we have long and short format. We'll go through this one just to address the differences between both of them. And in 4G the waveform, in uplink we used to have only one single carrier of DM, and in downlink you used to have all of DM. Like now in uplink, this is the main differences. It can be single carrier or even all of them. And actually, if you remember that the single carrier of DM, this is the main point of this one, was to reduce the peak average to power ratio, PAPR, peak to power ratio. But now in 5G is giving some advantage that you can, with whenever you are very close to the site, having a very good radio condition, you can take, for example, of DM up to 2 carriers and so on. So this can give some advantage in the uplink speed and so on. And also it can be dynamic. This is I think it's based on the vendor specification or whatever, but this is like now whatever have been introduced by 3GPP. And the last part, it's about the modulation. The last part in this slide, the modulation actually in 4G, the uplink was the baseline, 64 pound. but still now it's being supported 250 QAM in 5G in the later versions and for the 3GPP and also the later devices. But as for 5G as a baseline, it's 250 QAM for uplink and downlink. One of also the points which I didn't highlight it here is related to that data channel coding. In data channel coding, and the 4G was using turbo coding, while the 5G is using LDBC. Uh, and this LDBC, this one actually it can offers it can offer like reduce the AU power consumptions. Also, that can improve the code modulation and so on. And for the control channel, we used to have something 4G, something called polar, and now in 5G we have it's called sorry in 4G it was we could tail betting demodulation code, while in 5G it was now called polar, and also this is offers much better code demodulation. This is as per the theory. So this is I didn't highlight the last part here in the slide because it's not covered in the slide. Uh, and from my point of view, it's not that important to just keep it as for information as a theory, but we are not like using in our daily basis or in our daily optimization. So this is overall technology. Now let's go through most of these points just to explain it more and explain it further to make it more clear. Okay, now let's go through the first part, which was highlighting the difference in the bandwidth. First of all, as mentioned, that the 4G bandwidth was supporting maximum 20 megahertz, while now the 5G is supporting two different frequency ranges, which is frequency range 1, sub 6 gigahertz, up to 6,000 mega, and you have the frequency range 2, and this is the available bandwidth per each frequency. For example, frequency range 1, it's can supporting 5, 10, 15, 20, up to 100 megahertz, and this is based on 3GPP release, which mentioned below. And the second one, it's about the FR range. It can support starting from 50 megahertz up to 400 megahertz. And this is the main thing that now the 5G is supporting up to 20 times compared to the 4G, and also having new spectrum definition, which was never used before in 4G. For example, is midwave or FR2. Second part, which is very important actually, it's related to that the NR, as mentioned here, offers less guard band and higher spectrum utilization compared to 5G. Okay, it's mean one of it's two things actually. The first, the 4G band, if you remember, it was symmetric in the both sides. Both sides should have equal distribution. For example, in total, you have 10%. Should be in both sides very equal. You cannot have different or cannot have a symmetric guard band. While in 5G, the first point which need to be addressed, now you can have asymmetry. You can have a different guard band in the two different sides as per the specification, 3GP specification. Second part, that now the guard band itself it's reduced. It's become from 2 to up to 5% only compared to 5G. So to 4G. 4G was 10%, which is actually offering much higher spectrum efficiency or spectrum utilization compared to 4G. And this is just like example for some of the available bandwidths, and each of like what kind of the spectrum utilization you can use, how much of the spectrum or how much from the channel bandwidth can be used. As you can see here now that it can go up to 97, 98% for different bandwidths and so on. And before for 4G, it was fixed to 90%. So this is the first part here for the 5G bandwidths. Now let's move forward. Now let's have a quick comparison between the frame structure in both 4G and 5G. Then I will go through the 4G part first, then we can spot the differences. So the first part, it's about the frame structure. The frame structure in 4G, it was 10 milliseconds as a total duration, and this has remained the same in 5G as well. And the frame structure in the one frame was consisting of 10 subframe. This 10 subframe each was 1 millisecond. This has also remained the same in 5G. So now let's go quickly through the 4G, then we can spot the difference between both of them. Okay, in 4G, the first point here that the subframe was the minimum unit of scheduling, which means that the scheduling unit in 4G was around 1 millisecond. And this subframe, as a subframe structure, we used to have 2 slots. Each slot was having around 7 symbols if you're thinking about normal cyclic prefix. Now, in 5G, we use, and also in 4G before going to 5G, in 4G we used to have a fixed subcarrier spacing, which is 15 kilohertz. Now in 5G we have different type of, first point, we have different type of subcarrier spacing, which allowing us to have a different slots per frame. So the first point is about the scheduling unit. Now the scheduling unit in 5G, it became with it become by slot, not by subframe. And the number of slots within the subframe, depending on the subcarrier spacing. For example, 15 kilohertz, this means one subframe equal to one slot. So this means that in case of subcarrier spacing 15 kilohertz, this means you will have the scheduling unit will be 1 millisecond, which will remain same compared to the 4G. If you're speaking about 30 kilohertz, which is the standard, which majority of the network using in C-band, we have 2 slots per subframe. So this means the slot, one slot duration will be around 0.5 millisecond, which have the duration of the subframe, which means now you'll have more faster scheduling if you're comparing to 4G by almost half, because now your scheduling will be based on the slot, which is 0.5 millisecond. And the more you go, like the more you increase your subcarrier spacing, the more you will have more slots, the less you will have slot duration, which means that you will have better latency. However, this can be associated with another drawbacks, like for example increasing reducing the coverage, increasing the interference, because the more increasing this one, the more your guard band will be reducing. So as a summary, to summarize this one, the first point here, that frame structure, frame and subframe duration remain the same for 5G, no differences. And the second point, the number of samples in a slot, is now fixed to 14 samples. Before in 4G, the slot was consisting of 7 samples. If you're talking about normal circuit prefix, now it's increased actually to 14, and it's fixed to 14. So third point, it's about the subcarrier spacing. Now you have in 4G we used to have a fixed subcarrier spacing, which is 15 kilohertz. Now the 5G allows actually different configuration, and up to 240, but now we are speaking like supporting up to 120 kilohertz, because 240 is mainly used for the control channel in milliwave. So if you're talking about 15 to 100 kilohertz, so this change of flexible numerology, this is actually allow more flexibility on, or less change in the slot duration, because actually the slot duration mainly equal 1 divided by the subcarrier. So the more you increase the subcarriers, this means you will have less slot duration. This means your scheduling will be more faster, because you have your scheduling unit now in 5G is based on in our slot. And number 4, that 5G is now using a slot, as I just mentioned, as a scheduling unit instead of subframe compared to 4G. That's why the more subcarrier spacing, the faster the scheduling. The last part, that the number of resource grid, or you can see resource element within the 5G resource block, is increased by almost double, because of the same point that now we have fixed number, the slot is say fixed number of symbols in 5G, which is around 14, and the 4G is 7 symbols. That's why the number of resource element is being increased for the resource block, one resource blocks compared to 4G. And this is the main differences for the frame structure. Now let's go through high-level comparison between the physical channels and physical signals between 4G and 5G before going into some details for some of those channels or signal or physical signals. So initially you can see here in the first part, in the physical channels, we have a physical broadcast channel, and physical broadcast channel in 4G and 5G almost having the same function. But broadcast channel is now being combined within the SSP block in 5G. This is the main difference. And secondly, we have the PDCCH, which was part in 4G, and this indicates or stand for physical control format indicator. And this was mainly used in 4G to provide information about the number of samples is going to be by PDCH. For example, 1 sample, 2 samples, 3 samples, and so on. And this information and this channel now is being no longer used in 5G, it's being removed. And this information, the same information can be included now within the master information block message. You can find here the information about how many samples is going to be used by the core set and so on. And after, or by the PDCH. After, we have PHICH channel. This is physical arc indicator channel. And if you remember this one, it was being used in 4G as to give the acknowledgement or non-acknowledgement for the physical shared channel data for the uplink. So now it's not being no longer used in 5G, and all this information is being sent in the uplink DCI in NR now. After we have the PDCH, it's almost having the same function for 4G and 5G. However, it will be highlighted in more details in next slides. That just like there is a new concept called core set being introduced in NR, and it's just a core set. This is just giving you more control over the frequency domain resources. If you remember 4G, the PDCH was using the entire system bandwidth. However, in 5G now it's not the same. We have something called core set. We'll go through the details of it in the next slides. Then after you have the PDCH, physical downlink shared channel, and PRACH, physical random access channel. This is almost having the same function in both of them. Then PDCH also, the physical uplink control channel. It's almost the same function. However, in 4G now introduced something called short PDCH. Before in 4G we have long PDCH only. Now we have long and short PDCH, and this PDCH was being introduced just to support the low latency application, and also this one will be covered in different slide just to show the main difference between both of them in more details. Then if you're talking about the physical uplink shared channel, it's almost having the same function with no change. Then moving forward to the physical signals. If you're talking about the synchronization signals, primary and secondary synchronization signals, it's exactly the same function, no main differences, except that first part that now the information or the BSS and SS also then now is being combined SSP along with the broadcast channel. And if you're talking about the BCI calculation, now the range of BCI is increased in 5G almost by double. If you remember, as I remember, 4G was from 0 to 503. I think now 5G become from 0 to 1008, as I remember. So that's just a BCI number or whatever is being increased. Because if you remember also, the BCI is a combination between BSS and SSS. Then moving forward for the reference signals, if you are speaking about cell-specific reference signals in 5G and in 4G, this was used mainly to demodulate the channel condition and so on. And we used also to have DMRS for PDSCH for the 4G. Now this in 5G, there is no longer 5G is no longer cell-specific reference signal. We don't have this concept anymore. It's like we call it CRS free. There is no more cell-specific reference signals. However, we have now DMRS associated with every channel. Like we have DMRS for broadcast channel, we have DMRS for PDCH channel, we have DMRS for PDSCH channels, where they can be used to demodulate the channel or the radio condition through this. And the main difference also that the CRS was always on, cell-specific signal. It means that it's all the time transmitted across the complete bandwidth. However, the DMRS is not the same situation. And also we have the channel state information reference signal. This is also can be used for the channel demodulation and so on. And now also we have one more concept being introduced, which is the BTRS. This was not one more reference signal. I mean, this was not before exist in 4G. It's just being introduced in BTRS in 5G, and actually this is referred to the phase tracking reference signal, and this is it's more required for phase noise estimation and compensation, especially in the mid-wave and the higher frequencies. This is actually mainly it's allow the UE to estimate and subsequently compensate for both phase noise and frequency offset. It's kind of long story, will be covered maybe later in other sessions, but it's not here. Just here I address that it's not covered in this slide because here I just address the main differences that this reference signal was not before existing 4G. Now let's go through some of these points in details. For example, the differences in broadcasted channels, PDCCH, also PUCH, and other also the reference signal and so on. Then let's cover it in more details. Okay, moving forward. Now let's go through the downlink comparison for the PDCCH, physical downlink control channel, to visualize the differences between 4G and 5G, just to make it more clear. Okay, the first part of 4G, if you can see, if you're assuming that you have your frequency domain here in the left, and this is a time domain slots, and you can see now that the PDCH is being like distributed across the complete bandwidth, and then you will start like detecting the PDCH resources, but for this is from the complete bandwidth. It's always distributed across the entire system, as you can see here. This is used always across the entire system. While now going to the 5G, now 5G it's actually have introduced something called core set. And actually, the core set was introduced in 5G to accommodate the new concept of the bandwidth part, which is being highlighted before. And this actually gave more control for the frequency resource allocation compared with LTE. As mentioned before, LTE is giving the across the entire system bandwidth. Now you have more control over the frequency domain resources or allocation. So this actually can free some resources to the shared channel and so on. And for the time or the symbols, it's remained from same 5G remains same as 4G, 1 up to 3 symbols. So now this is the main differences between the 4G. It's very simple between 4G and 5G. And just to summarize or to sum it up, that the 5G 4G PDCH, it was distributed across the entire system bandwidth, while there is now the 5G is giving more control over the frequency resource allocation. Thank you. Now let's move to the next part. Okay, now let's go through the uplink comparison for the physical uplink control channel, PDCCH. Okay, as you can see here from this figure, this is the uplink channel bandwidth for the 4G. As you can see that PDCCH is being transmitted in one or more resource block. Okay, and this is being at both edges of the band, as you can see here, and the number of RBs is based on the configuration and also based on the number of users. So this is actually it's long format, like because wide cone long format only supporting one type, which is long format, because it's all the time at 1 millisecond. It cannot be less than this. And you can see here the distribution of the users. User one was taking one, for example, 1 RB from the first slot here. Then here it's the slot changes because here we are assuming that the frequency hopping is enabled, and this is actually one of the things which can maximize the frequency diversity. So in summary, that 4G having a long format, which is using 1 millisecond, and also the frequencies is being distributed across the edges of the bandwidth. This is the first point. Now going to 5G, as mentioned before, it's supporting now two different formats. The first one is short format, and second one is long format. And the short format, when you talk about short and long, it's just speaking about the symbol duration or the duration of the symbols. The short format supporting 1 up to 2 symbols, and this actually can give you much better latency. Why? Because now in the short format, you can see the PDCCH feedback can come or can be allocated within the downlink feedback. For example, it's coming directly after the PDCCH. So once you have this one, you don't have to wait for a long time or for the uplink slots until you receive the acknowledgement or whatever feedback from the UE and the PDCCH, because as you know, the PDCCH covering many information. So this one actually shortened the feedback from the UE, so accordingly it can improve the latency. And it can be 1 up to 2 symbols as shown here. And also still the 5G supporting long format, which is 4 up to 14 symbols. And this one actually is being transmitted only in the uplink slot. And the PDCCH still it's having a close concept to the 4G, which is also transmitted across both bandwidths, as you can see here, the channel bandwidths at both edges of the channel bandwidths, and it's covering 4 up to 14 samples. And here actually this is the overall table of format which we have it currently in 5G. We have PDCCH format from 0 up to 4, and each one having a different number of symbols according to the specification. For example, format 0 and format 2, this is related to short format, and format 1 and 3 and 4 is related to the long format. So just to summarize, the main differences is that now the 5G introduces short symbol, which can play a big part in improving the latency. That 5G now support two different format, and this format having more flexibility and support for different use cases. Why different use cases? For example, now we can use in the mobile broadband, we can have long format, same as what we have for 4G. However, for example, if you are talking about another application, for example, in the future for ultra reliable low latency communication, in this case, you need to have a much and quicker, faster feedback. So in this case, you will need maybe to go through the short format. And also for sure it will have another disadvantage, but for the latency point of view, it's much better to go for the short format. That's it for the PDCCH part. Now let's move forward. Now we will go through the differences in the synchronous signal and broadcast channel between 4G and 5G. Initially, we'll be like presenting this, assuming this is a frequency domain, and this orange line is the center frequency of the 4G, and this line is the center frequency of the 5G. So now the main difference is actually between the broadcast channel and synchronous signal, that in 4G it was all the time fixed at the center in the bandwidth. It cannot be changed. This is the main point here. While in 5G we have more flexibility now. It can be configured at any location, at the end of the band or the center of the band, or also it can be configured at the start of the band. And actually you need to keep this point into your mind because it's very important. One of the most recommended actions for the SSP is about the frequency domain location. It's being recommended to keep it in the center, especially in the beginning of the band, because actually, as you know, that the 5G having higher bandwidth, and the UE need to blindly decode the SSP location during the initial or during cell search. So if you kept at the end of the bandwidth, especially the higher bandwidth, 100 megahertz, 1 megahertz, and so on, especially in the blind detection during 5G standalone, this might longer the time until the UE detect, and this might increase your latency. Plus, also it can increase the power consumption and so on. So now you have this like flexibility to configure it at any location of the within the 5G channel bandwidth. And also one more important point just to highlight about this part, that as you know that the SSP has maximum of 20 resource blocks. The reason of designing this one is just to accommodate with the minimum, as you know that we have bandwidth part also, and the minimum UE bandwidth can be 25 megahertz. So the SSP cannot cross this. That's why they make it up to 20 RPUs only. Yeah. Let's move next to the next part about the SSP. Okay. If you remember in the table which we addressed before, that we mentioned that in 4G we used to have this kind of broadcast channel. It's like in 4G it's wide beam, while in 5G it's narrow beam. If you remember, if I addressed this SSP beam swimming and so on. So okay, this is actually the main differences here. As you can see here, the 5G is distributing this one across. It's like a wide beam, while the 5G having its narrow beam. And you can see now that in 5G, for example, it can improve the first of all, can reach more edge users, much higher, much better coverage. And also this like reducing the interference between this one, because narrow beams, like everyone will having a dedicated narrow beam, every users, so this can improve your quality. And this is how the SSP beam swimming is working. Assuming this is the same users and he's moving across within the same cell, and is being changing the SSP. For example, here we will be reporting 8 SSP beams. For example, SSP1 till SSP8. So this like reading, the UE will read all the SSP's measurement, and then he will report it to the NLP. So he will be choosing SSP1 because now this is the most nearest one and address or towards this particular UE. So they will have much better coverage. This domain is for this one presenting the coverage point of view or RSRB. As you can see here, this is a signal strength and this is the time. So once the UE moved towards other SSP, for example, SSP4, this like UE would be reporting SSP4 as the best coverage and best quality as well, and so on. So this one actually can improve the coverage and the quality in 5G. So this is one of also the main differences between the broadcasted channel between 4G and 5G. Let's move next. Now let's cover the part related to the reference signal differences between 4G and 5G. If you remember in the table, I highlighted that the 5G is no longer using the cell-specific reference signal. It's called cell-specific reference signal free, or CRS free. Okay, because in 4G we used to use the cell-specific reference signal to modulate the channel condition. So through the reference signal, and as you know that in 4G reference signal is being transmitted all over all the time being transmitted, we call it always on, and also through the entire bandwidth. So this one increasing the chance of having more extra overhead compared to 4G to 5G. I will explain the differences from where it's coming And this is the first point. Second point also, that we have higher risk of interference in 4G, because this is always on and also consuming more resource and so on. So now let's first go through the calculation of the overhead of 4G. As you know, in 2T2R we have around 16 resource element, as showing here, for in every of those symbols is being reserved for the reference signal. So if you divided this one by the 12 subcarriers for the resource block multiplied by 14 symbols, so at the end you will end it by 9 to 10% overhead. And also again, the cell specific reference is being transmitted over the entire bandwidth of the 4G. And if you're speaking about 44R, you will have extra 8 resource elements. So in total, you will have around 14% overhead. And if you are speaking about TM9, you will have around another additional 12 resource elements. So your overhead will even further increase up to 16 to 17%. This is the first point. So the overhead of the reference signal is really high. Now comparing to the PDSCH DMRS. Okay, first of all, PDCCH DMRS, it's having two types. It can be type 1 and type 2. Type 1 having more resources compared to type 2, as you can see here. For example, if you are speaking about only single symbol, so the single symbol, it can consume minimum 50% of the resource element within the symbol. 50%, that every second resource element can be used for resource. And this is if you're speaking about, for example, rank one user consuming rank 1, or in case of rank 2, we have something called, we can go through these details later on also, whenever you are going to cover this section in 5G. If you there is two things in the DMRS. There's something called code division multiplexing and something called frequency division multiplexing. The code division multiplexing, for example, here I mentioned we have 4 ports. So for example, if you are using port 100, 1000 and 1001, these 2 ports can code division multiplex it in case of rank 2. So in case of rank 2, this is the overhead you can get. Rank 2 or rank 1, you can get up to 3.6%, which is almost less than even 3 times if you are comparing, or half if you are comparing to the 2T2R, which can offer rank 2 to in case of 4G CRS. So this is the first point, and this number can increase by double up to 7.2% in case if you are using rank 4, because if you are using rank 4, in this case you will be utilizing all the resources inside here, all the 4 ports. So in this case, this means there will be no more longer resources remain for PDSCH. So for this, I mean for this particular sample. So in this case, your resources will be increased by double compared to the rank 1 and rank 2. And also this in case of multi-user MIMO. Multi-user MIMO also, if you assume that you have 4 PERD users, each user is using a single port. So again, you will not have more channels remain for resource element remains for PDCH. So again, your overhead will be maximum 7.2% if you are speaking about user using rank 4 or about multi-user MIMO for 4 paired users. This is the first point. Second point about this part. Here I mentioned that the cell-specific reference signal is being transmitted over the entire bandwidth. Here this is not the case. Here this is the PDCH DMRS is associated with the number of resource blocks used by PDCH, because DMRS is always coming with PDSCH. So let's assume that you have 10 resource blocks only being assigned to a single user. So this means your DMRS will be only transmitted across those 10 resource blocks. So this is also one of the advantages, which can have much less interference compared to the 4G. And this is over. And the same concept being applied for the others. This is just showing the different type of configuration and overhead. For example, here if you're talking about double symbols and type 2, type 1 with double symbols, your overhead will increase by double. And here if you're speaking about type 2 is actually using much less overhead, because this one consumes about 33% only from the symbols which is being used for the DMRS. And for sure, this will, again, if you're using type 2 with double symbols up to 12 ports, this will be around 4.8%. So you will have less interference in all cases compared to the 4G. Less overhead, I mean, compared to the 4G. So let's move forward and see the next section. Moving forward, this will be the last part in today's session. This like slide will be addressing all the key differences or be highlighting the key differences in link budget between 4G and 5G. Overall, the methodology is almost the same. The calculation methodology of the link budget is almost the same between 4G and 5G. And simply link budget, if you remember, it's just accounting all the gain and losses from the transmitter toward the receiver through the medium. And this medium can having a gain and losses and so on. And the simple link budget calculation that the received power equal the transmitted power plus the gain, any gain here, for example, antenna gain, minus the losses in between. This is the link budget calculation. And I will be showing the formula at the end of the slide here. And I will attach the complete working materials to the link, the YouTube video below. You can just find it in the link description, in the YouTube description. So now let's go through the overall module or overall calculation methodology. This is a BTS, for example, transmitted power. You might have some cable losses. This is depending you're using, for example, AH or using RRH. Then you will be adding the antenna gain. Then you'll be considering all the losses in between. Then at the end, you will be adding the UE antenna gain, and this will be your last received power calculation and so on. So, okay, what is the main differences? For example, if you're speaking about the milliwave, there is few items need to be considered because milliwave is more sensitive because of very big higher frequencies, so it's more sensitive. So, for example, you need to consider the body blocking loss, rain slow margin, and so on. This need to be can be considered in our calculation, and also anything like flash loss as well. So this need to be considered for the midwave. Okay, as a summary for the link budget, main consideration, for example, the cable losses. As you know now, in 4G we are using RRH or RU. Now in 5G we are moving towards AU or AS, right? So this one actually doesn't, it's almost having no cable losses. While here before in 4G we used to have some cable losses. So this is one of the factors which can add up to the 5G. While the BTS antenna gain for the typical antenna it was from 15 dBi up to 18 dBi. Now for the 5G, for the active antenna, if you're speaking about 64 to 62R, it's about 25 dB. And the propagation model changed. Before we was using Okumura and Costa Hata for 3G and 4G. Now we'll be starting using UMA, RMA, and UMI. This is like stand for urban macro, rural macro, and urban micro. And for the maturation loss for 4G, it was relatively small, and 5G it will be higher. You will have higher penetration losses, and this is because of the higher frequencies, which you are, for example, for the C band and for the milliwave and so on. The interference it was higher in 4G. It can be, you can consider it's less in 4G and 5G, and this is mainly because you have now more narrow beams. For example, you have more narrow beams, so this can improve your quality and the interference. So this as just a summary. For example, here I'm just addressing what means by OTA. This is over the all interface. And here I address that we have this few concepts or few items which can need to be considered, especially for the milliwave. And here is a simple calculation formula for the link budget. And thank you very much for your time for today. And please, if you like the video, press like and subscribe and share it with your friends. And see you next session. Thank you.